Okay, in this chapter, we'll study inductors. Okay. So we'll see like capacitors stored energy in electric fields, inductors store energy in magnetic fields. Okay. This chapter is an application of this equation, Faraday's law that you studied last time. Okay, you saw that time-varying magnetic fields produce electric fields. Okay, and this chapter is essentially an application of this equation. Okay, so let me illustrate this. What you'll be seeing. Okay, you saw that. Yeah. So let's say you have a wire, circular wire, and you pass a current through this wire. Okay. So if you use your right hand and if your fingers curl around in the direction of the current, this will produce a magnetic field like so. This will act like a magnet like that. Okay. Now here's the deal, here's the relationship to the Faraday's law. Now if you increase this current, what will happen? What will happen if you increase the current? The magnet gets stronger, so this magnetic field increases, and here's a time-varying magnetic field. By changing the current, you've changed the magnetic field. And then if you have another sensing coil like this, okay, the magnetic field through this coil increased, and so that'll induce a current in this coil, in the sensing coil. And you saw that what this equation tells you is, so curl E equal to minus del B by del T. Okay. So as the magnetic field through this coil increases, there's an electric field induced, and the electric field induced is such that the current in this opposite direction, which is trying to oppose the magnetic field that's producing it. All right, so changing current changed the magnetic field, which induced a current in this sensing coil. Okay, so that's essentially a lot of applications we see, well, is based on that. Okay, so changing currents change this magnetic field, which will induce an electric field here, which will induce this current in that sense. Okay. And so what happens is, so if you take a coil of wire, this is a solenoid, and if you increase the current in this solenoid, the first ring will induce an EMF in the second ring, induce a current in the second ring in the opposite direction. Okay, so what this does is, if you just take a straight wire, okay, so if you take a straight wire like this, well, just take a straight piece of wire and try and increase the current in it. There's no problem with increasing current, but you take the same wire and wind it into a solenoid. Now, if you try and increase the current in this wire, it fights the increase. Okay, so its property changes. The same wire, if you just wind it into a coil like this, now this guy does not like changes in current. It doesn't like increases in current or decreases in current, and it'll fight that. Okay, so those are some of the properties we'll study. Again, it's an application of Faraday's law. Changing time-varying magnetic fields induce electric fields. Okay, so mutual inductance is an effect. Okay, so if you have a coil here, you change the current in this coil, it changes the magnetic field that it's producing, and it'll induce a EMF in nearby coils. Okay, so often magnetic flux through a circuit changes because of time-varying currents in nearby circuits. So if you have a time-varying current here, it's changing magnetic fields, and the flux through this coil will change. So often magnetic flux through a circuit changes because of time varying currents in nearby circuits. This process of induction is called mutual inductance. So it will induce an EMF in this nearby coil. Time varying currents in this coil is affecting nearby coils. Okay? Mutual inductance can be a nuisance in electric circuits, since variation in current in one circuit can induce unwanted EMF in nearby circuits. Okay. And nowadays you have many circuit elements in small areas on chips and stuff like that. Okay. So time varying currents here will induce EMF there. Okay. Now it can be nuisance and it can be useful as well, this phenomenon. So the most important useful application of mutual inductance is in transformers. And we'll talk about transformers. They're used to step up and step down voltages. Okay. Induction stoves are an application of that, and they are the most efficient stoves. So we'll talk about that in a second. Okay. All right, let's define mutual inductance. Okay. So mutual inductance is time varying currents in one circuit is inducing an EMF in nearby circuit. Okay. So the EMF induced in the nearby circuit is proportional to the time varying currents in the first circuit. And this proportionality constant is called the mutual inductance. Okay. Now, oftentimes we can't give you the formula for mutual inductance. That's because this mutual inductance will depend on the configuration of the circuits, how far apart they are, and so on. Okay, so more often than not, we can't give you an expression for this. So, for instance, if you have this is I1T. Okay, so here's the current changing in this circuit, and if this is the second circuit, so E2 in this circuit will be quite different than if the configuration was like this. I1T, the induced EMF in this will be different than this, and with the same number of turns and all that stuff. So just the configuration will change it. Okay. Anyway, so the mutual inductance is is a reflection of how strongly these two circuits are coupled. Okay. So time varying currents in this circuit, time varying currents in that circuit is inducing an EMF in this circuit. Okay. All right. So I don't know if you're aware of induction stoves. You can go to Lowe's and places like that and buy these stoves. Okay, so induction stoves are about 90% efficient. Gas stoves are about 50% efficient. Electric coils, okay, so you've seen those heater coils and you put your pan on top of there. They're about 70% efficient, and electric gradient stoves are also about 70% efficient. Okay. So what are these induction stoves? Okay. So induction stoves, again, so they're just a coil where you pass an AC current through this coil. Okay, so when you pass a current through this coil, it is producing a magnetic field, and if the current is AC, then the magnetic field is, okay, so let's say here's the coil. When the current is like that, again, stick your fingers in that direction, and that will behave like a magnet, like so. And when the current is like that, this will be a south pole and a north pole. Okay, so in this coil, if you supply an AC current, then the polarity of this magnet will flip. And now, if you have a metal stove, a metal pot, in this metal, this changing magnetic field will induce a current. Okay, so as the strength of this magnet is increasing, it's inducing a current in this direction. Okay, induced current. So when you apply an AC source to this coil, the changing magnetic field induces a current in the pot, in the bottom of the pot. And what happens to the current in a resistance? It turns into heat. Okay, so all the energy here is transmitted here, and none of the intermediary stuff gets heated up. That's why the induction stove is most efficient. All the energy is transferred directly to the pot. Okay. So here is the AC source applied to this coil, which induces a current in this pot, and that gets turned into heat. Okay. So the induction stove is the most efficient. So what's the deal with this induction stove? What is the only drawback? It only works on metal appliances. Okay, so it has to be a conductor. Yeah. That's how wireless charging works as well. Okay, so you have a transmitting coil. A transmitting coil, it's just a coil, and you apply an AC voltage to it, and you have a receiving coil, and it induces a current in the receiving coil, and that's an AC current as well, and that has to be converted to DC before you can charge your battery. Okay? So the wireless charging pad contains a transmitting coil, and alternating current through this generates a fluctuating magnetic field. Okay? Your device also has a coil of wire. Okay. And when the device is placed on the charging pad, the fluctuating magnetic field on the pad induces a current in the device. A rectifier converts AC to DC. Okay, we'll look at the rectifier circuits in a couple of chapters. Yeah. So, so here's a electric vehicle charger, wireless electric vehicle charger. So here's an AC. So this is saying 90% grid to battery efficiency. So, okay, so here is an AC pad. Here's the receiving coil. This is an AC voltage that gets rectified, and then the DC voltage is sent to the battery to charge it. Okay. So wireless charging efficiency falls between, it's about 80%, with newer models reaching closer to 90%. Wired charging often sees efficiency of 90 to 95%. Okay? So you lose out about 5% efficiency, but I guess for the convenience, you're willing to sacrifice that. Okay. All right, now we'll talk about self-inductance. Like I said, if you take a wire and coil, wind it around like this, okay, and here's what happens. Okay, now if you have a straight wire and you want to increase the current in the straight wire, there's no problem. You can easily increase the current in the straight wire. Now let's see this guy. If you try and increase the current in this guy, okay, this coil will produce an increasing magnetic field, and the neighboring coil there will be an induced current in the opposite direction in the neighboring coil. So here's this straight wire that once wound into a solenoid, it fights changes in current. Okay, if you try and increase the current, so if you try and increase the current, it induces an EMF in the opposite direction. fighting this increase in current. Similarly, if you try and decrease the current, it'll induce an EMF fighting that decrease and will try and increase the current. All right, so this wire, when it's wound into a solenoid, has acquired the property of able to fight changes in current. Okay, it doesn't like changes in current. Okay, an opposing self-induced EMF develops as the current increases or decreases in an inductor. The self-induced EMF is proportional to the time rate of change of current in the inductor. All right, so if you try and increase the current in this coil, it'll induce an EMF in the opposite direction. And if the current is decreasing, it'll induce a EMF in the opposite direction, trying to maintain that current. Yeah. Okay, the induced EMF, this EMF, is proportional to the time rate of change of current. Okay. Notice, if the current is steady, if the current is not varying with time, the induced EMF is 0. Okay. So this thing only fights changes in current. So if the current is steady, then the EMF is 0. And this is self-inductance. Okay, so this is the induced EMF in the same coil while the current is changing. Mutual inductance was induced EMF in a neighboring coil due to changes in current in close-by coils. Okay. So, all right. So this is the self-induced EMF. Okay, it's proportional to the time rate of change of current, and this self-inductance for a closely wound coil, for a closely wound solenoid of n turns, the self-inductance is mu naught n square area of cross-section times the length of the solenoid. So this is the volume of the solenoid. And little n is the number of turns per unit length. Okay. So this self-inductance, the proportionality constant, how strongly it can fight changes in current, is given by that. The units of inductance are called henries, after Mr. Henry. And if you put all those together, it's volts second per ampere. Oftentimes you want to increase the self-inductance, and the way to increase the self-inductance of a coil is stuff it with magnetic materials. Okay? If a ferromagnetic material is placed inside the solenoid, its inductance can be increased considerably. Okay? So you can increase the inductance, and thus mu naught gets replaced by mu m. Okay, so you can increase it by a factor of 100 or so easily. All right, so here is the symbol for an inductor. Okay, so you take a coil and wind it up into a solenoid, and it's now become an inductor. Okay. And again, what are the properties of this guy? It doesn't like changes in current, so it will smooth out fluctuating currents. It doesn't like changes in current. And also you learn that it stores energy in magnetic fields. Yeah. And so this is a very important piece of equipment. Okay. So one of the things that an inductor does in a circuit is to oppose variations in currents through the circuit. So if currents change in this circuit, it opposes this. Okay, so if you place this in an AC circuit, the higher the frequency of the AC circuit, the greater its resistance will be. And we'll study that in the next chapter. Okay. So in this circuit, here's a DC circuit. Here's the EMF source, a resistance, and an inductor. When you close the switch, okay, if this guy was not present, when you close the switch, the current will go from 0 to maximum value. Okay, so without the inductor, the current will go from 0 to its maximum value instantaneously. With the inductor present, here's what happens. With this guy present, now when you close the switch, instead of going to its maximum value instantaneously, it goes exponentially. Okay, so the presence of this guy delays the increase to maximum value. The maximum value is still the same as that before. Okay, the maximum value is E over R, E over R. Yeah. It's just that that increase has been delayed, the time to maximum value. Okay, so that's what this guy did. Okay, so one of the things that an inductor does in a circuit is oppose variations in current. So when the switch in the circuit shown is closed, current does not rise instantaneously to steady state value. Yeah. So it'll rise gradually like this. Okay, so now we want to see how this current rises. Okay. And so what we'll do is we'll model this system. So when you close the switch, you have a closed loop, and Mr. Kirchhoff tells us that the sum of the voltages across the elements in this circuit should add up to 0. So if we start here, when you go across here, it's plus E. Then you're flowing with the current. That's the change in voltage across this is minus IR. Okay. And then as the current is increasing, this guy is opposing it. This end is positive. So when you go across there, the current is minus L di by dt. Okay. So Mr. Kirchhoff says that these three terms should add up to 0. Okay, so the behavior of this system is modeled by this differential equation. Okay, so using Kirchhoff's law, we were able to come up with a mathematical model. And you can solve this differential equation. Here's a solution to this differential equation. So the current in that circuit is this given by this function. IT is E over R, 1 minus e to the power of minus t over tau. So the current is rising exponentially. At t equal to infinity, this goes to 0. And the steady state value is E over R. The steady state value is E over R, as if this guy was not present. Okay, so this is an ideal inductor. It has no resistance, so the maximum current is E over R. E. Okay. And the time constant is given by L over R. So greater the time constant, greater L, greater the time constant, slower the current will rise. Okay. So greater the value of the inductance, the slower the current will rise. Okay. So current in an RL circuit builds up exponentially rather than instantaneously as for a purely resistive circuit. Okay. So now we'll see the following. Let's look at the following. All right, in this circuit, when the switch is over there, a current goes through like this, and current builds up exponentially, and eventually it gets to be a steady current in this circuit. And then what we're going to do is we're going to remove the battery by flipping the switch from there to there. Now, if this guy was not present, when you flip the switch, the current would instantly go to 0. But with this guy present, what happens is when you flip the switch from here to there, this guy has some energy stored in it. Okay? So the current was going like this, and when you flip the switch, this current tries to go to zero, but this guy has some stored energy, and he will drive a current keep driving a current like that. Okay, so the current won't go to zero instantly. He'll drive a current as long as he has energy stored in him, and then once he uses up all the energy, then the current will go to zero. Okay. All right, so let's, here's another diagram of that same circuit. Okay, when this switch is closed, the current builds up through here, gets to a maximum value. Once the current has reached its maximum value, what we're going to do is we're going to open this switch and close that switch. By opening that switch, you're removing the battery. And then you're closing this switch. And you're doing this simultaneously. Okay. So when you remove the battery, this current wants to decrease. So this guy will become positive and try to maintain a current in the same direction. Okay. So here was with this switch closed, here the current flowing, and once it's reached steady state, what we're going to do is we're going to remove the battery, open this switch and close that switch. And when you close this switch, the current wants to die, but this guy will maintain the current for a little bit. Okay. So once the EMF is removed, the current in the RL circuit is given by that. Okay, so it maintains that current for a little while. That current dies exponentially, but it maintains it for a little while. Okay, the equation for just this loop is, okay, so the current was in this direction, and once it's closed, it'll maintain a current in this direction. Okay, the current is in this direction. Let's go from here and go in this direction. This is plus IR, and then this guy was positive and this guy is negative. It should be minus the voltage across this, but the voltage across that is L di by dt. Okay, and di by dt is negative, so minus. So you take a positive value. This term is negative, so IR minus and plus this term is 0. Okay. And so here's the differential equation for this circuit once you remove the battery. And the solution to this is is the exponential solution that you saw. I di by dt is equal to minus R over L I. And IT is so that's the solution to that equation. And that's what this is. Okay. And I naught is just E over R, the initial value of the current. All right, so you saw that this guy is able to store energy, and when you remove the battery, he will pass a current through this circuit for a little bit till he runs out of the energy that is stored in him. Okay, so let's see how much energy is stored in him. Okay, and the energy stored in this guy is in the form of magnetic fields. Okay, a solenoid. You guys remember that a solenoid, when you have a steady current flowing through the solenoid, there's a magnetic field in there. Okay. And if you check your last chapter, the strength of the magnetic field is that. Mu naught N is the number of turns per coil, and I is the current flowing through this thing. So that's the strength of the magnetic field. All right, so we'll see energy in the magnetic field. An inductor, an inductor resists an EMF from establishing an instantaneous maximum current in the RL circuit. When you close this guy prevents the current to go from 0 to maximum value instantaneously. So what is happening is the battery does work to establish a current. Okay, the battery is doing work to establish that steady state current, and in the process stores energy in the inductor. Okay. So let's look at that. So when you close the switch, the equation Kirchhoff tells us plus E minus IR minus LDL by dt, L di by dt. Okay, and we'll bring these two terms on the other side. E equal to IR minus plus L di by dt. And then let's multiply both sides by I. Okay, the reason we did this is, see, this is the rate at which the battery is delivering power. This is the rate at which this load is dissipating power. Okay, so this is the rate at which power is being delivered. This is the rate at which power is being energy is being dissipated in this resistor. Okay, so rate at which power is delivered, rate at which power is dissipated in the load, and this term can be written like as di by dt of 1/2 Li squared. Okay, so the rate at which power is delivered, this is the rate at which power is dissipated in the load, and this is the rate at which power is being stored in this device. Okay, so earnings, the rate at which you're earning is the rate at which you're spending plus the rate of your savings. So the energy stored in an inductor at any given instant when the current is I is this much, 1/2 Li squared. Okay, so this is just like any other expression that you've seen. Kinetic energy was 1/2 mv squared. Potential energy in a spring was what? 1/2 kx squared. Energy stored in a capacitor was 1/2 CV squared. Okay, so just like that, here energy stored in an inductor is 1/2 Li squared. Okay, and in a second we'll show that this energy stored is in the form of a magnetic field. Okay, so now we'll give you the expression for energy density in a magnetic field. So here's a coil. When you pass a current through this coil, it is producing a magnetic field in. All right, so the energy stored is 1/2 Li squared. L is the self-inductance of the coil. And if you substitute this value there for L, so the energy stored is 1/2 mu naught N A L I squared. Yeah. But the magnetic expression for the magnetic field is mu naught Ni. So there's an I squared terms there, there's a mu naught, and so this can be combined to give you B squared divided by mu naught N. Okay. So, this is N squared. Okay. N square, I square, mu naught square, so divide by mu naught square, so that can be written as B square over 2 mu naught, and then you have 2 times the volume. Okay. So the energy stored is this expression times the volume of the solenoid. So this is the energy density in the magnetic field. That is the energy per unit volume in magnetic fields. Okay. So whenever you create electric or magnetic fields, this is the energy density in the field. So the energy density, U for energy, subscript B telling you it's a magnetic field. The energy density is B squared divided by 2 mu naught. Yeah. So anytime you have a current passing through a solenoid, that current is producing a magnetic field, and in that field you can think of as energy stored in that magnetic field. So now we'll consider one of the more important applications of mutual inductance. Okay, so here's the deal. This is the symbol for an AC source. You take an AC source and pass this AC current through this coil. The coil will, of course, produce a magnetic field, and this is a magnetic material, soft iron. What this does is it sort of channels this magnetic field through this coil. And as the current in this thing is changing, the magnetic field is changing. And this changing magnetic field will induce a current in this coil. Okay. So an AC source coupled to this coil through this magnetic material. The magnetic material is just concentrating the magnetic field, improving the efficiency. Okay, so the changing current is inducing an EMF here. And the voltage induced here, V2 in the secondary coil, is N2, the number of turns here, divided by N1, the number of turns in the primary coil, times V1. So if the number of turns here is 100 times greater than that, then the voltage in the secondary coil is 100 times greater than the voltage in the primary coil. So you can have 50 volts in here, a 50 volt amplitude input signal, and you'll get a 5,000 volt amplitude. Yeah. So transformers work only for AC currents. Okay. So what's going on? So if this is 100 times greater than that, the output voltage is 100 times greater than the input voltage. Are you getting free lunch? We all know the answer to that. So what's going on?
Does it use energy from the other coil?
Okay, so power input is equal to power output. And power input is V in current in equal to V out current out. Okay, so when the output voltage increases by a factor of 100, the output current decreases by a factor of 100. Okay. Now this is under ideal conditions. Some energy is lost in the heat there in hysteresis, but in ideal conditions, that's what's happening. Okay. Okay, so now this is an extremely important thing. So there are more than trillions of copies of this circuit. Okay, so this is a very fundamental circuit. When do you have oscillations? When can you have oscillations? So let me show you a system that has oscillations. We've seen this okay, when does a system oscillate? When there are two different forms of energy. You need at least two different forms of energy. Okay, so it has potential energy and kinetic energy, and the system will oscillate when the energy goes back and forth from one form to another. And of course, when energy is conserved, you don't want, you don't want mechanical energy to be dissipated. Okay, so for a system to oscillate, you need at least two different forms of energy, and where an energy is not dissipated. Okay, well, let's see. I had another. Okay, never mind. Okay, so now let's make a system like this. We'll make an LC circuit. We'll make a circuit where it has a capacitor and an inductor. What does a capacitor do? It stores energy in the form of electric fields. What does an inductor do? It stores energy in the form of magnetic fields. Okay, so now we have a system that can store energy in two different forms. Okay, so let's charge the capacitor. Let's store energy in the capacitor, and okay, so and then we'll store energy in the capacitor and let the system go. Okay, when you store energy in the capacitor, what this will do is this will drive a current through this inductor. Okay, and as this drives the current through this inductor, this energy is being transferred to energy in the magnetic field. So as current is flowing through, energy is being stored in magnetic fields. So energy is transferred from there to there. And eventually this capacitor is completely discharged. All of the energy is stored in the magnetic field. And then this magnetic field will drive a current through here and charge the capacitor. And eventually it will transfer all its energy to the capacitor. And then back and forth. And now this will do the same thing in the opposite direction. Okay. So you see, in this system, when you charge this, store an energy, it'll drive current like this, current like that, and then back the current will go in the opposite direction. So this system is oscillating back and forth. Okay. How long will it oscillate?
Forever if it's not losing energy.
Forever if it's not losing energy. In an electrical system, what makes it lose energy? Resistance. Okay, so in an ideal circuit, in this circuit there's no resistance and it'll oscillate forever. Okay. And this system has a frequency of oscillation. The natural frequency of oscillation is 1 over LC. We'll show that to you in a second. Okay. So that's the frequency of oscillation of this guy. And this guy is at the heart of all wireless devices. So there's trillions and trillions of this circuit in your lives, okay, in the world. Okay. So let's show you this expression. So the energy stored at any instant in the inductor is given by that. The energy stored in the capacitor at any instant is given by that. Okay. And in this ideal system, the rate at which the total energy is being dissipated is 0. Okay, so in this ideal system, d by dt of that is 0. Okay, so you get an expression for the charge and the capacitor. Here's the differential equation for the charge and the capacitor. Okay. By the way, I is dq by dt, and that's how that expression, to go from there to here, you'll need this. Okay. Now this is an easy differential equation to solve. This is one of the basic ones that you solve. We'll call this omega square. Okay, so the equation is d square q by dt square plus omega square q. Okay. And the solution to this differential equation is that. Okay. So omega is the frequency of oscillation. This is just the phase constant. Okay. And I, the current in that circuit, is also oscillatory. All right, so there's the frequency of oscillation, 1 over L root of LC. All right, so that's the natural frequency of this oscillator. Okay, so how is this used in a in a wireless device. Okay, so what you do is you use the phenomenon of resonance. Okay, so here's this LC circuit, and now we are indicating the resistance. This guy will always have some resistance. So here's the resistance in the circuit, and here are the rabbit ears antennas. Okay, so this circuit has a natural frequency. All right, the resistance modifies the frequency. But anyway, this guy has a natural frequency. And resonance is, if you excite this at its natural frequency, you can set up large amplitude oscillations. Okay. So let's say this guy has a natural frequency of 100 megahertz. Okay, 100 megahertz. What kind of signal is this? These are FM radio bands are in that. Okay. So right now in this room, how many FM signals are there in this room? There's many, 20, 30 FM radio stations. All their signals are in here. 90, 97 megahertz. I'm not going to. 98 megahertz, 100 megahertz, 101 megahertz. Okay. All those signals are there. When you excite at a frequency that doesn't match the natural frequency, that signal will not set up a large current. This frequency the signal whose frequency matches this natural frequency will set up a large amplitude current. Okay. All these other signals are setting up very small currents. Only this guy sets up the largest amplitude current. Okay. And then what you do is you couple this signal via mini transformer, and then this is the processing circuit. Okay. So you catch the signal using this tuning circuit. So this is how you listen to a wireless signal. So at the heart of every wireless device is this circuit. So you pick up an electromagnetic signal using this tuning circuit, and then couple it to a processing circuit via a mini transformer. Okay. So like I said, there are trillions of copies of this circuit everywhere. It's your cell phone has that circuit and all that. So tuning circuits take advantage of this natural frequency with a phenomenon of resonance. All right, now we'll show you, you've seen this sort of thing before. What does the presence of resistance do? Resistance dissipates the energy. Okay, so we'll show that the charge on the capacitor decreases exponentially. Okay, so now how do you get an equation modeling the behavior of this guy? So here's the equation. Okay, this is the energy stored in the inductor. This is the energy stored in the capacitor. And because of the presence of this resistor, this energy stored, total energy stored is changing. It's decreasing. So the rate at which the energy is decreasing is the rate at which it's being dissipated in the resistor. Okay. And so if you rearrange all of that, here's the differential equation you get. And you've seen this differential equation before when you set up this guy. Okay, so that differential equation is very similar to this differential equation, okay, for the motion of this mass damped oscillator. Okay, and so if you solve this differential equation, here is the solution. Okay, and you see the charge on the capacitor is decreasing exponentially. Okay, so just charge on the capacitor is decreasing exponentially as the energy is being dissipated. Okay, and the new frequency at which it oscillates is modified by the presence of the resistor. Anyway, so this is the frequency with of the oscillator with the resistance present. Okay. So you have a expression for the frequency of this guy, and as long as the driving frequency matches the natural frequency of this guy, you set up a large amplitude oscillations. Okay, so again, this is at the heart of all wireless devices. So that's the mechanical equivalent, parallel of this electrical equivalent. Okay, so these two guys behave equivalently. This is the mechanical version, and here's the electronic version of the oscillator, of a damped oscillator. All right, so that finishes this chapter.